Yeah, no. Why? On my, the one I just was, when I changed back to
Because when it comes as a bunch, which it was, there's a lot of baby's breath and this one, so I did that, and that's a pound, a couple and a half.
Oh, thank you, Rebecca. Sir, we've had 4 years. I just think like a statue made or something.
Of me.
They are not flowers. Like a statue.
That's 6 years with me.
Yeah, but we
No,
were 4 years.
Come on, ladies, please, if you're logging on. Right. When you want. Just leave it there and go on the line. Okay, thank you. We've got to do this to start with, otherwise we'll be here forever. Go to the Moodle, please. Just do that quietly, please, while I give you the theory behind it. Now, yesterday we had a look at the 3 different types of spectra. The first being a continuous spectra, and a continuous spectra is created by a hot body which is heated up in such a way that it will start to glow. And a hot body being a solid, or what's the other option? Right, it's a gas under extreme pressure. The liquid glowing would have to be a liquid of a metal. Okay? So if you heat water up, for instance, it won't eventually glow. Okay, it will do something before it does that. Okay. The second is when you get an absorption spectrum, and it looks like this here. It's a continuous spectrum underneath. And finally, there. And what is the what's seen above it? Black lines. There are missing frequencies of lines. There are missing wavelength. Now remember, if I say frequency or wavelength, it's either way I can describe the photons that are missing. And the last one is the emission spectrum, which is the exact opposite of that, which is a black box. It's a black spectrum, and all we see over the top of it is the lines. Oops. So yellow is missing there, green is missing there, and blue is missing there. Okay? And if these are linked spectrums, in other words, they come from the same source or they're around the same source, they would be caused, this here and that there would match. Okay, so this here was missing an orange, and that would be where the orange has ended up. Is that okay? So the emission spectrum and absorption spectrum for a situation normally match up if they're from one situation. Now, we need to explain why this happens. And to do this, we are going to have a look at the way that photons, which are pieces of light, particles of light, how they interact with electrons. Now, we all know from, oops, don't tell me that, what happened? Oh. That's what I wanted to do. We all know from junior school that this is the current baby model of an atom. Okay? And we're going to use the baby model because it's the easiest one to know and work with. We have a nucleus about which is orbiting what? Electrons. And the electrons are arranged in what? Shells. And the inner shell contains 2 orbits. Then the next set of shells contains how many orbits? 8. Now I can't do all 8 here, so I'm just going to put that and continue on, pretend there's 8. Okay? Now, electrons normally occupy given orbits, but they're allowed to change their orbits. They're allowed to jump from one orbit to another. So if an electron is in this orbit here, for instance, let's go to black. Let's go to black. Okay. And the orbit above it is free, and there is no electron in that orbit. It's able to jump to that orbit if it is given enough energy. Now, how can it get some energy? Well, one of the ways we can give the energy is we can somehow zap the electron somehow. We can give electricity to the gas. Okay? Or, even easier, we can send in a beam of light. And if we put in this beam of light, which contains different colours of photons, so that's a blue photon. Okay, when I get the idea that's a photon. Photon is a particle which is also a wave. Okay? And we know that every photon, according to Planck's law, every photon of light has a different amount of energy. And that energy is dependent upon its frequency. So this is a blue photon. I'm going to do a diagram of a red photon. Okay. And let's do a yellow photon. Enough yellow photons. And let's put a green photon on. Are you okay with me saying green photons? These are pieces of light of different frequencies, and therefore they have different amounts of energy. Of the colours of photons here, which of the photons would have the biggest amount of energy? The blue. Good, because it has the highest frequency. Okay? Here's a photon that you can't see. You've got to imagine that's a UV photon. Okay? You can't see that photon. That would have the most amount of energy. Now, an electron, if a blue photon, just say for instance, to get from here to here, it needs to absorb exactly 1 blue photon. Okay? So here is the blue photon coming in, and then the electron absorbs that. And it jumps from one orbit directly to the other orbit. It can't jump halfway, so it can't absorb a red photon. A red photon won't allow it to jump. It's not enough energy. But imagine a blue photon does this. So it will jump up and it will now start to orbit at the higher level. Okay, are we okay with that? So we all, at the moment, the electron is orbiting at the bottom level. Then suddenly, a piece of blue light comes through and strikes the electron and gives it enough energy to jump up to the second orbit, to the next orbit up. Okay? At which it then starts to orbit at the higher level. Now, we call this an excited electron. An electron can stay as excited for a length of time as it wants to. There is no set rule how long it must stay excited, and we don't know how long it will stay up there. It might stay up there for a few moments in time, up to hours in time. Eventually, it will have to release that photon back. And just say that it was travelling. Let's put our photon back up here. This is our electron. Okay. Imagine it was travelling this direction at that moment. It would release the blue photon in this direction. Off it would go. As it releases that blue photon, what would it do? It would drop down to the lower orbit, its original orbit. Okay? And the original orbit is called the ground state. Okay? Are we okay with what it does? So, in comes a photon. If the electron can use that photon to jump to a higher orbit, and that orbit is free, you can't have two electrons can't be in the same orbit. So it can jump to that orbit, it will absorb that photon. Can it jump halfway there? No. Could it absorb a yellow and a green photon and then get there? The answer is no. Because it's going to only absorb one photon per jump. Are we okay with that? It can't take two photons and give that, like saving up to get to there. Because it can't just jump halfway and then get another jump. It doesn't transit as well. The electron instantaneously disappears from the lower orbit and instantaneously reappears in the higher orbit. There is no transition between the two. There is no electron leaving this orbit and coming to here. It just disappears from one orbit and reappears in the others, as if it's been transported there miraculously. Are we okay with that? Right. Imagine if the photon here absorbs, rather than the blue photon, it now absorbs the ultraviolet. It doesn't have to just jump up one orbit. No, it can jump up a number of orbits. So I want you to imagine that if it absorbs this ultraviolet here, it can jump up to this orbit. Okay? When it jumps up there, it will start to orbit at this higher orbit. How long does it stay in this higher orbit? As long as there's no want. It's not as if it's a sentient being. Until the energy fluctuations, the entire universe suddenly makes it come out. So what it does is it will be up there for a period of time. We can estimate how long it will stay up there, but it's all probability. Eventually, it will start to give up that photon. If it absorbs a UV photon to go up there, that's that grey one, what could it give out to jump back down? Right, the same UV. Imagine if it's over here, however, it would be going that direction. Okay? So it scatters the photons. However, does it have to give out the same photon that it came in with? No, is the answer. It can jump its way back down. Imagine it just jumps down a little orbit. It can give up the photon for that orbit. And that photon might be a red photon. Then it might jump down to that level there and it might give off a green photon. So it might take in a UV photon, and as it goes down each orbit, it only gives off the amount of energy that it needs to drop down to the next orbit down. Does that make sense? What photons? We don't know. So what I'm saying here is, imagine if this is the ground state. We're going to call the ground state n equals 1. And imagine there are n equals 2, n equals 3, n equals 4 possible orbits above this ground orbit. Is that, everyone happy that's a ground orbit? So an electron is in here at the moment. If it absorbs a photon, let's imagine it absorbs a photon that it can jump up to n equals 3. How many possible pathways can it come back down with? It could go fully back down, or it could go 1, 2. How many possible photons could it re-emit on the way back down? 3. By the way, I've got these equally spaced. They shouldn't be equally spaced. That's a different photon to that one. Okay? For every arrow, it's a different photon. Okay? I want you to imagine, I'll do a better one this time. So here's my n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Okay, you should notice that they're getting small, closer and closer together. Okay, imagine you do 5. So you absorb a photon that you can jump to orbit number 5, which is quite far out of the outside the high in the atom. Okay, okay, you're a way away from the nucleus now. So you used to be in here. There's my nucleus. You used to be there at n equals 1. And now you're out here at n equals 5. So you've jumped a way away from the nucleus. Okay? How many different photons can you emit? Now, to get there, you've absorbed how many photons? 1. How many different photons can you emit to get back home? Well, for those people who are in year 11, sorry, not in year 11, you're in year 11, they go some 3 unit, you can do this by counting permutations. But it's even easier if you just do what we call arrow diagrams. You can just emit 1 coming back, or you go 1 there, then 3 back, or you could do 2 there, 2 there, 3 there, 1 there. Okay, that's 2 jumps home. This is 1 jump home, these are all 2 jump homes. Or how about if you do 3 jumps home? You could do that, then that, then that. Or you could do that. Can you see how many? This is one of your exercises that you're going to have to do. You have to work out how many photons are the thing. But this photon here and this photon here are the same. So that's yeah. Okay, so it's a combination. It's actually a combination, yes. Now, so are we okay with what happens? So let's actually have a look at what will happen and what your applet is going to do that you're going to work through. We're going to be using the simplest atom, and the simplest atom for this to happen is the hydrogen atom. Okay? And you're going to shine. You're going to shine white light in there. You're going to follow the applet in. Now, white light is every different colour coming in. And they're all going to be parallel. So let's put some orange photons in. And let's put some yellow photons in. Okay, green. Let's just blue, blue. And some ultraviolet. And even some heavy ultraviolet. That's sunburny stuff. Okay? Rightio. So imagine all the colours of the rainbow there. There's an infinite different light. Okay. Now, as it comes in, where will I get all these photons over here from? White light. What's producing white light? A continuous spectrum. A continuous spectrum produces white light. Now, the different colour of white is up to you. We've got yellow white, which means it's slightly more green. We have white, which is an A-class star. We've got yellow white, which in all those are a yellow star. They're all white light because they're all continuous, giving me all of the different colours of the rainbow. So this is a continuous spectrum over here. Continuous spectrum is all the photons are possible and none of them are missing. Okay, now there's not just one atom of hydrogen here. There is a whole lot of hydrogen atoms. Okay? And therefore there is a whole lot of electrons that can jump to higher orbits. Now, as it goes through, imagine this one here, let's go back to red, this electron here absorbs a red photon and it goes up to there. So imagine red is the one colour that they can all absorb. Okay? What colour is going to be missing when it comes on this side? Red. Red. You have all the other colours, but red will be missing. So we'll have some grey. We'll have some orange. We'll have some yellow. We'll have some green. We'll have some blue. Okay. But what colour is going to be missing?
Red.
Red. Where did the red happen? What happened to the red photons? Right, they're absorbed over here. They're with the electrons. Okay. Now, what would this look like? Now that looks like a continuous spectrum. So over there,
Absorption.
this one over here looks like this. If you were to do a photographic spectrum of it, you would see it look like that. Oops, wrong colour. Come on, you can change to cyan. That's it. Right. Over there, you would see all of that. Okay? Now, on the other end, look. Come on. On the other side, what would be the thing that is missing?
Red.
Red. So you'd have the same spectrum over there as on that side as on this side, but you would not have the red. What would the red appear like?
Black.
Right, not black, absent. Now what colour is the absence of light?
Black.
Black. Okay, in fact, absence of light is the colour of the surface. So that's how these black lines get. Now, if we're only absorbing a few types of red, are all the red photons the same frequency? No, there's a whole range of frequencies. Imagine if it's only this red that is absorbed. So you get only a single line. But what other colours could also be absorbed? This one and this one. Imagine that there are different, because this is just to the first orbit, it could also be jumping to a higher orbit, and so on. Are we okay with that? Right, now let's have a look at imagine it's absorbing red, green, and this blue. Where do those colours end up? Now they end up with the electron whizzing around in all directions. But wherever the orbit was, wherever the electron is in its orbit, it will release it in that direction. So if the electron is here when it releases the photon, it will send the photon that direction. Is that clear?
Yeah.
If the electron is travelling this direction, at this moment, it will release it that direction. So what would happen, what would you do if you were to try and work out the spectrum over here? So we're just here, we've got an eye, here's my eye. Okay? And my eye is a camera, and that camera is taking a spectrum. I would see a black background, and instead what I would see would be, I would see this red photon, I would see this green photon, oops, green photon. See that green photon has been absorbed over here as well. What else colour? And the blue photons were also absorbed. Are we okay with that? So what is this one over here called? An absorption. So you'd see an absorption here, but what would you? An emission. So let's just summarise that. If I produce a continuous spectrum over here, and I shine my light through a gas, this is my continuous spectrum. Don't worry guys, you'll be doing a huge amount of taking notes on this. Okay? As it goes through, as that light comes through the gas, what will appear over here? An absorption. Okay, so if you look through a gas at a glowing body, you will see an absorption spectrum. Where would you have to situate yourself to actually see the emission spectrum? Anywhere that you can't see this body. So I want you, if you look through this direction, so you look up there, so you don't see that, you will see an emission spectrum. If you look directly back at this, you will see an absorption. Are we okay with that? Rightio. Now, what you're about to do is you're going to use the applet which you see underneath there. So I'll just top this off now because there's no need to do that.